Greetings to our curious listeners, and welcome back to the Deep Dive. This is the show where we take complex sources, break them down, and hopefully pull out some essential knowledge and maybe even surprising insights for you. Last time we talked about transformers, their incredible success, sure, but also some critical limitations, especially when you're dealing with really, really long sequences. We sort of touched upon why a new frontier in sequence modeling isn't just, nice to have, but maybe even necessary for where AI is heading. So today we're embarking on a foundational journey. We're diving into the world of state space models, or SSMs. We'll explore their origins, trace their evolution a bit. Specifically, we're focusing on two really pivotal advancements. First, HiPPO. That laid some crucial theoretical groundwork, particularly around online compression. And second, the structured state space model, or S4. That's what really transformed SSMs into something computationally efficient and, frankly, empirically powerful. You've given us a great stack of research papers and articles here, and our mission, as always, is to extract the key nuggets, help you get up to speed on these fundamental concepts quickly. Let's get started. Okay, Section 1. The genesis of modern state space models. HiPPO. To really appreciate where SSMs are today, I think we need to go back to the conceptual roots, specifically to HiPPO. That stands for High-Order Polynomial Projection Operators. It sounds complex, and it is, but it represents a pretty significant theoretical leap. So at its core, what problem was HiPPO trying to solve? What's the central challenge here?
Right. HiPPO addresses a really fundamental problem in learning from sequential data.
Yeah.
How do you represent the history? And not just represent it, but continuously update that representation as new data streams in. Especially online, think about it, data keeps coming, you need to understand the cumulative past without forgetting important stuff.
In previous approaches, like standard RNNs, they struggled with this, right?
Oh, absolutely. RNNs were, notoriously difficult. Limited memory horizon was a big one. They just couldn't remember things far back. And then you had the vanishing and exploding gradients problem, making training on long sequences really unstable.
Even the fancier ones, like LSTMs and GRUs.
Even LSTMs and GRUs, yeah.
Yeah.
Their gating mechanisms were clever heuristics, definitely an improvement. But they often needed you to specify upfront some kind of prior about the sequence length or the time scale you expected, which meant if the data suddenly changed speed or length outside that range, their performance could just tank, not ideal for dynamic real-world data.
Okay, so how did HiPPO approach this differently? You mentioned it reframed the problem.
Exactly. HiPPO reframed it as an online compression problem. That's the key conceptual shift. Its innovation is compressing continuous signals or even discrete time series by projecting them onto polynomial bases.
Polynomial bases, like fitting a curve to the history.
Sort of, yeah. Imagine data points forming a curve over time. Instead of storing every point, HiPPO finds the best polynomial approximation of that entire curve up to the current moment. And as new data arrives, it updates the coefficients of that polynomial. So you have a compact, evolving summary of the history's shape, its information content.
Okay, that makes sense. Continuous compression, not just discrete token memory.
Precisely. It's about summarizing the function generating the data over its whole history.
And the sources highlight one specific variant, HiPPO lag scaled Legendre. What makes that particular one stand out?
HiPPO legs is really important because it provides an optimal solution to this online function approximation problem under certain measures. Its real strength is that it always considers the function's full history. It doesn't use a fixed-size sliding window like some other approaches.
Like the leg T, translated Legendre, that the papers also mentioned.
Exactly like leg T. Leg T uses a fixed window, and that makes it incredibly sensitive to the window size you choose. The sources mentioned that even a tiny error, like 0.5% in setting that window length, can lead to massive approximation errors. Just completely impractical.
Wow. Okay, so HiPPO legs avoids that by looking at everything.
Everything. That full history aspect is what gives it timescale robustness. This is huge. It means you don't need to fiddle with hyperparameters about expected sequence lengths or timescales. It just adapts.
So if the data speeds up or slows down,
Theoretically, it doesn't care. Dilating the input signal doesn't change the underlying approximation coefficients, and even the discrete recurrence relation you use to implement it is invariant to the discretization step size, the delta t.
that's a big deal compared to RNN gates, which can be super sensitive to that step size.
A major benefit. It offers this inherent adaptability to different sampling rates, different resolutions, without needing retraining. Very versatile.
This theoretical elegance is fascinating. But did it actually work in practice? The sources mentioned some impressive empirical results when HiPPO legs was used in RNNs.
Oh, definitely. The theory translated very well into practice. The empirical validation is quite strong. On the permuted MNEST benchmark, for example,
Mm.
that's a tough one for long-range dependencies because you shuffle all the pixels.
Right, you lose all local structure.
Exactly. HiPPO legs achieved a new state-of-the-art accuracy there, 98.3%. Showed it could capture those non-local relationships.
And what about that trajectory classification task mentioned? That sounds more like real-world data.
Yeah, that was very telling. It involved classifying trajectories, but crucially, they tested robustness to out-of-distribution timescales and missing data. And HiPPO legs blew away the standard RNN and neural OD baselines. We're talking 25–40% higher accuracy.
25 to 40%, that's a massive jump.
It really highlights its practical advantage when data isn't perfect or predictable, which is, most real-world data.
So this brings up a question. How does HiPPO relate to other memory mechanisms we know, like the LMU or even the gates in LSTMs?
That's one of the really insightful parts of the HiPPO work. It provides a unifying theoretical framework. It turns out you can derive the Legendre memory unit, LMU, directly from HiPPO principles in just a few steps. The LMU is essentially HiPPO using a specific fixed window.
Ah, so LMU is a special case.
A special case, yes. And even more broadly, HiPPO sheds light on the gating mechanisms in LSTMs and GRUs. It shows how their forget and input gates can be seen as approximations that arise when you only use very low-order polynomials in the HiPPO framework.
So it's like HiPPO is the more general, principled foundation.
Exactly. It provides this deeper understanding and generalization, and direct comparisons like signal reconstruction tasks.
How did it fare there?
HiPPO legs outperformed standard LSTM, LMU, and even a combined LSTM plus LMU model. It reduced the normalized mean squared error by over 30%.
30% better reconstruction fidelity. That's significant.
It really is. Yeah. It solidified HiPPO's potential, not just as a theory, but as a practical building block for better, more robust sequence models. It moved beyond heuristics to something mathematically grounded.
Okay, section 2, bridging theory to practice. The structured state space model S4. So HiPPO laid these strong theoretical foundations: online memory, timescale robustness, optimal compression, really powerful ideas. But turning that into a general practical and maybe most importantly efficient deep learning model was the next big challenge. And that brings us to S4, the structured state space model. Now, before S4, there were attempts like the linear state space layer, LSSL. It showed promise, right? Hints of potential.
It did. LSSL was conceptually neat. It tried to combine that continuous time HiPPO idea with RNN and CNN characteristics. It could capture long-range dependencies better than many models at the time.
But the sources highlight a critical but. What were the limitations that held LSSL back? What did S4 need to solve?
The but was enormous. LSSL was fundamentally computationally infeasible for practical deep learning.
Infeasible how? Too slow, too much memory.
Both. Massively. The core computation, calculating the latent state, required O(n) squared L operations. N is the state size, L is sequence length.
N squared L, that scales really badly.
Terribly. And memory wasn't much better. O(n) times L. Think about a typical state size, maybe N256. Even for moderately long sequences, you're talking orders of magnitude more compute and memory than an RNN or CNN of comparable capacity.
So it just wouldn't fit on GPUs or run in reasonable time for the kinds of problems people wanted to solve?
Exactly. It hit a wall very quickly. Training times would be prohibitive. Memory would explode. It couldn't scale.
And wasn't there also an issue with numerical stability, even if you could compute it?
Yes, that was the other major hurdle. The special A matrix derived from HiPPO, while mathematically elegant for the theory, is what's called highly non-normal in linear algebra terms.
Non-normal, meaning?
Essentially, it means it behaves badly with standard numerical algorithms. Small errors can get amplified exponentially during computation, leading to instability, nan-ns, things blowing up.
Okay, so even theoretically, faster algorithms proposed for LSSL didn't work reliably because of this underlying matrix property.
Precisely. The non-normality blocked the use of conventional techniques that assume well-behaved matrices.
Right. So the challenge was clear. Take this theoretically powerful but computationally crippled model and make it efficient and stable. That's what S4 set out to do.
That was the core mission of S4, and it succeeded remarkably.
How? What was the key innovation? How did S4 break through that computational bottleneck without just throwing away the HiPPO foundation?
The core innovation in S4 is a novel parameterization of the state space matrices, especially that problematic A matrix from HiPPO. Instead of using the HiPPO matrix directly in its raw, non-normal form, S4 reparameterizes it. It cleverly decomposes the matrix
Decomposes it how?
into the sum of two parts, a low-rank term and a normal term. This is the technical magic,
Okay. Low rank plus normal. Why does that help?
because each part can be handled efficiently and stably using different techniques. The tricky low-rank part can be dealt with using the Woodbury identity.
The Woodbury identity. A matrix inversion trick.
Exactly. It lets you efficiently compute inverses involving low-rank updates.
Yeah.
And the normal part of the decomposition is, by definition, well-behaved.
Yeah.
It can be diagonalized stably, which simplifies computation dramatically.
So you split the problem matrix into two manageable pieces.
Right. And the truly elegant part, what the sources call the magic, is that when you combine these operations, the whole thing mathematically simplifies. It reduces to computing a specific type of structured kernel, a Cauchy kernel.
A Cauchy kernel.
Yes. And computing Cauchy kernels efficiently is a well-studied problem. You can use algorithms based on the fast Fourier transform, FFT, especially when you view the SSM as a convolution.
Ah, connecting it back to convolutions and FFTs, that sounds much more efficient.
Way more efficient. This whole reparameterization strategy bypassed the LSSL's issues completely. It made SSMs practical.
So let's unpack the practical improvements. What did this mean in terms of speed and memory? What could researchers actually do with S4 that they couldn't before?
The gains were huge. S4 achieved A, n plus L computation. The tilde means ignoring log factors, and ON plus L memory.
N plus essentially linear scaling in both state size and sequence length?
Basically, yes.
Yeah.
Which is about as good as you can hope for in sequence models. It's computationally very scalable.
And compared to LSSL?
Compared to LSSL, S4 is up to 30 times faster. And the memory saving was staggering. 400 times less memory usage.
400 times less memory. Wow.
Yeah. And critically, this wasn't a trade-off. S4 actually outperformed LSSL empirically. Better performance, vastly better efficiency.
That's the dream combination.
Really unlocked the potential. It meant SSMs could finally compete.
And this efficiency also made it more versatile, right? The ability to switch between representations.
Absolutely.
Yeah.
S4 can efficiently switch between its different views. There's the continuous representation, ideal for modeling signals like audio directly. There's the recurrent representation, which works like an RNN step-by-step, making it efficient for inference or autoregressive generation. And there's the convolutional representation, using that FFT-based computation, which is incredibly parallel and fast for training on GPUs.
So you can train it like a CNN, but run inference like an RNN.
Essentially, yes. You get the best of multiple worlds, and it's inherently adaptable, for instance, changing the sampling rate of your input data. In S4, that just corresponds to modulating the internal SSM parameters, particularly the step size.
No retraining needed just because the data resolution changes?
Often, no. It demonstrates this deep flexibility that many other architectures lack.
Okay, Section 3. S4's versatility and empirical prowess. Efficiency is great, essential even. But the real test is performance on actual tasks. And this is where S4 seems to have really made a mark. The sources paint a picture of S4 as a real powerhouse across different types of data. Let's start with the long-range arena LRA benchmark. You mentioned it briefly. What is LRA, and why were S4's results there so significant?
The LRA is a benchmark suite specifically designed to kill models that can't handle long sequences. It's brutal. Sequence lengths go from 1,000 up to over 16,000 steps, and the tasks require diverse types of reasoning, similarity, structure, even visuospatial reasoning on flattened images. It really pushes long dependency modeling to its limit.
And S4?
S4 didn't just do well. It basically set a new standard on LRA. It outperformed all 11 transformer variants they tested against, and other follow-up models too, on every single task.
Every task. Wow, what was the average accuracy?
It averaged 80.48% accuracy. Compare that to the baselines, none of which even broke 60%. It was a massive leap forward for long-range modeling.
Was there a specific task where it really shone?
The most famous one is PathX. This involves finding paths on a 128 by 128 image flattened into a sequence of 16,384 pixels.
16,000 steps.
Yeah, and all previous models had failed this task. They either ran out of memory, took too long to compute, or just couldn't learn the dependencies over that distance.
And S4 solves it.
S4 solved it. And when they visualized the learned convolutional kernels inside S4 for PathX, you could actually see filters spanning the entire 16,384 pixel length in the higher layers.
That's incredible. Direct visual proof it was learning those ultra-long-range features.
Exactly. Lower layers learned local stuff, higher layers aggregated globally. It showed it could handle these extreme sequence lengths effectively.
So it conquered the synthetic benchmarks. But what about real, messy, raw data? Did S4 strengths translate there?
That was a key question. Could this SSM approach handle raw signals without needing lots of pre-processing like feature extraction? And the results on raw speech classification were really compelling. They used the speech commands dataset, specifically the SC10 subset. S4 achieved 98.3% accuracy, working directly on the raw audio waveform.
Directly on the waveform, no MFCCs or anything.
No standard feature extraction, and that 98.3% outperformed all the baseline models that did rely on heavy pre-processing like MSCCs.
So the model learned better features from the raw data itself than handcrafted ones.
That's what the results suggest. A powerful long-range model can extract more information directly. It also beat a specialized raw audio CNN, the waveGAN discriminator.
How did it compare in terms of size?
That's the kicker. S4 achieved this with 90 times fewer parameters than the waveGAN discriminator and with fewer built-in architectural assumptions.
90 times smaller and better performance. That speaks volumes about its parameter efficiency.
It really does. And it showed that robustness to sampling rates, too. They tested it at half the frequency on speech commands without retraining just by changing the internal step size. And it still got 96.3% accuracy.
Very adaptable. Okay, so images, raw audio. What about language? That's the domain where transformers have been utterly dominant. Could S4 compete there?
That was the next big test. On Wikitext 103, a standard language modeling benchmark, S4 got very close to transformer performance in terms of perplexity.
Perplexity being the measure of how well it predicts the next word.
Right. With similar parameter counts around 250 million parameters, each S4 got a test perplexity of 20.95. The transformer baseline was 20.51.
So very close. Competitive.
Very competitive on quality. But where S4 showed a massive advantage was generation speed.
How much faster?
60 times faster. S4 could generate text at 48,000 tokens per second, compared to the transformer's 800 tokens per second.
60 times. That's a game changer for applications needing fast inference, like chatbots or real-time systems.
Exactly. That inference efficiency is a huge selling point for SSMs like S4.
And this efficiency carried over to other areas too. Time series, images again.
Yes. On time series forecasting, S4 outperformed the Informer model, a specialized transformer for time series, in most settings, 40 out of 50. It did particularly well on the longest prediction horizons, like reducing error by 37% when forecasting weather 30 days out.
Better long-term predictions make sense given its long-range strengths.
And on sequential CIFAR 10 classifying images pixel by pixel in a long sequence, S4 got 91% accuracy without data augmentation. That was competitive with a much larger 2D ResNet, which got 91.12% compared to S4's older baseline of 89.46%. It also showed more robustness to things like normalization layer choices.
So across the board, long sequences, raw data, language, time series images, S4 proved to be a remarkably versatile and powerful sequence model. Okay, section 4, key insights and trade-offs of SSMs. The empirical results for S4 are clearly very strong. But beyond the numbers, the sources offer this really interesting analogy to help understand the fundamental difference between SSMs and transformers. It gets at their inductive biases. They say SSMs are like brains, while transformers are like databases. Let's unpack that. What does that analogy tell us about how they work differently?
It's a really helpful analogy, I think. It captures the core philosophical difference. Transformers are like databases. Why? Because their core mechanism, self-attention, effectively caches every element of its history. Every token gets stored, indexed, ready for precise retrieval later.
So they excel at recall.
They excel at exact memorization and retrieval. If you need to find a specific fact from paragraph 37 of a long document, attention is great at that. It treats every input as an item to be filed away.
But the downside?
The downside is that cache has a fixed size. Once you exceed the context window, that information just gone. There's a hard limit. They can't look back further.
Okay, so transformers, databases, great recall, fixed context. What about SSMs as brains?
SSMs are like brains because they maintain a finite-sized memory state, but use it to continuously compress all its history. They process inputs online, constantly updating this compressed summary state. They can't necessarily recall a specific arbitrary detail from way back with perfect fidelity, just like you can't perfectly recall every word from a book you read last year.
More like remembering the gist, the important patterns.
Exactly. They maintain an infinitely long, theoretically, but fuzzy memory of the past. It's compressed, summarized. And this design inherently lends itself to efficient, interactive, online processing. Streaming data is natural for them.
So finite state, but infinite fuzzy history designed for streaming. Brains versus databases? I like it.
It captures that core trade-off precision recall within a fixed window versus continuous compression over an infinite horizon.
So what does this mean for choosing between them? This difference in memory strategy must lead to different ideal use cases, especially thinking about the input data itself, its resolution, its semantic content.
Absolutely. It points to where each architecture's inductive bias shines. So where is attention, the transformer's core, most effective? The sources argue it works best on pre-compressed data, data that's already at the right level of abstraction.
Like patches in vision or tokens in language.
Precisely. Vision models use patchification. Language models use tokenization. These steps take raw, high-resolution data and chunk it into semantically meaningful units before feeding it to the transformer. If you try to feed a transformer data where the individual units aren't semantically meaningful, like raw pixels, raw audio samples, or even characters in text, its performance often degrades. It struggles to form useful representations from that very fine-grained input.
It needs that pre-processing step to create meaningful chunks first.
Right. Now, connect that to SSMs. With their continuous state and compression focus, they have a potential edge when the data comes in at these very high resolutions where attention struggles.
Like character-level language or DNA sequences or raw sensor data.
Exactly. In those scenarios, the model doesn't just need to process tokens. It needs to perform the compression itself. It needs to take that fire hose of raw data and abstract it into meaningful features.
And that's what SSMs are inherently designed to do.
That's their inductive bias. Compress fine-grained data into meaningful abstractions. They're built for that kind of continuous summarization. The sources even propose a kind of litmus test. An ideal architecture should handle sequences with lots of noise or filler sequences that have the same core information as a clean one, but are much longer without a huge increase in compute or memory.
Because it can compress away the noise?
Exactly.
Yeah.
SSMs, being compression-focused, should theoretically be better at this than transformers, which are recall-focused and might try to store all the noisy details.
And you mentioned the HiPPO initialization in S4 helps with this too.
Yeah, the specific HiPPO initialization used in the original S4, HiPPO legs, involves decomposing signals onto exponentially warped Legendre polynomials. This further enhances its ability to model very long dependencies and handle varying timescales found in continuous, high-resolution signals. It reinforces that strength.
This has been an absolutely fascinating deep dive into the foundations of state space models. We've covered a lot of ground, from the theory behind HiPPO, its role in online compression, achieving that timescale robustness through full history memory all the way to S4. S4 really seems like the practical breakthrough, turning SSMs into efficient, high-performing models that can handle diverse tasks. We saw its power on long sequences with LRA, its surprising ability to work directly on raw speech, and those impressive speed advantages in generation, even while staying competitive with transformers on language modeling quality. And I think we really underscored that key conceptual difference today. SSMs as brains, continuously compressing history, versus transformers as databases, caching details within a fixed window. That difference in inductive bias seems crucial, making SSMs potentially better suited for high-resolution, uncompressed data where abstraction is key.
It's a different way of thinking about memory and processing sequences, definitely.
Well, this dive into HiPPO and S4 is really just setting the stage. It's the foundation for what comes next in this new generation of sequence modeling. Next time, we're going to shift focus to Mamba 1. That's the first selective state space model that really started competing head-to-head with transformers on general language modeling benchmarks. We'll explore how its selective nature, its ability to dynamically filter information based on the input, allows for things like linear time inference with the constant state size, really pushing efficiency even further.
Mamba builds directly on these S4 ideas, but adds crucial new mechanisms. It's the next logical step.
Absolutely. So as you mull over today's discussion, here's a thought to leave you with. If the future lies in learning directly from raw, high-resolution data, as SSMs seem well-suited for, what other common pre-processing steps that we take for granted beyond tokenization or patchification might eventually become obsolete, replaced by models that can learn those abstractions themselves? Something to think about. Join us next time on The Deep Dive.